Hello everyone. In this video we are going to consider an example of designing a second order controller for a given system using the frequency response of the system and also the controllers. So for our system we have, as you can see over here in the description, we have the transfer function which represents the relation between the input of the voltage amplifier driving a DC motor and the angular velocity of the motor itself. So the plant is given in the form of a transfer function with 3 poles, as you can see over here, and there are no zeros. Now, by sketching the body diagram of L of S, we want to design a controller such that the controller is of order 2 or smaller, so it will be either a proportional one, a first order or a second order controller. The simpler the better. Steady state error will be smaller than 0.1 if we have the reference signal equal to R times step of t, where the amplitude of R is smaller than or equal to 3, and we have also the disturbance at the same time, which is in the form of a step function with d times step of t, and the amplitude of d is smaller than or equal to 7. So we need to consider both the reference signal and the disturbance signal. We need to have the crossover frequency omega c being bigger than 0.2 radian per second, so it should not be smaller than that. The phase margin needs to be at least 60 degrees. And for the noise and disturbance rejection, we have these requirements. Gamma n and gamma d are equal to 0.1 for omega n bigger than 2 and omega d smaller than 0.01 radian per second. And then we'll check at the end whether all these requirements are satisfied or not. So as the first step, we need to draw the body plot for the given system. In it, we will consider L of S equal to GC times GP, while GC is equal to 1. And then we'll define the forbidden areas for the noise and disturbance rejection. You can do it manually. It won't be a difficult one. We have only 3 poles over here with a constant term, which is 10. But to save time, I already have done it using MATLAB. So I have declared the plant as the G transfer function, and I have drawn the body plot for it. If I want to determine the dangerous zones for the disturbance rejection and noise attenuation, for the noise we need to have amplitude of L of j omega should be smaller than 20 decibels. For omega n bigger than 2 radian per second, and for the disturbance amplitude of L of j omega should be bigger than, for the noise we need to have it smaller than minus 20 dB, and for the disturbance we need it to be bigger than 20 decibels. For gamma d smaller than 0.01. Okay, and with them we can determine the dangerous zones for the noise and disturbance rejection. So omega n bigger than 2, we need to find out omega equal to 2, which is here. This frequency over here is 2. From that frequency onwards, we need to have the amplitude smaller than 20 decibels, minus 20 decibels. So if here we have the minus 20, I assume, we will have this dangerous zone for the noise attenuation. For the disturbance rejection, we need to have the amplitude of L bigger than 20 dB for frequencies smaller than 0.01. The frequency is here. And we need to have the amplitude bigger than 20 dB. So here we have the 20 dB. Therefore, this will be the dangerous zone for the disturbance rejection. So we can see that we are on the border. We need to increase the amplitude a little bit at least for the low frequency part in order to have the amplitude or the requirement on the disturbance rejection satisfied. In terms of the noise attenuation, we are fine for now. Now, in terms of the steady state error requirement, we need to have error smaller than 0.1 while we have R and D in the given form. Steady state error, considering both the reference signal and the disturbance at the same time, using the superposition principle, could be obtained in this way. So we will have it in the form of limit of S times the whole error as S goes towards 0. And for the E of S, we will have it in the form of E of S over R of S times R over S, because R is the step function, plus E over D times D over S, as the disturbance is also in the form of a step. And then we will have it simplified, and at the end we will get S of S times amplitude of R minus D as steady state error, and that should be smaller than or equal to 10 times S of S, because R minus D over here, we have the range of values for R between minus 3 and 3, the range of values for D between minus 7 and 7, and as a result, the range of values for R minus D will be between minus 10 and 10. I hope you could see it. Yeah? If R is equal to minus 3 and D is equal to 7, then the value will be minus 10. And vice versa. If we have R equal to 3 and D equal to minus 7, it will be 10. Therefore, we will have this. So amplitude of R minus D will be smaller than or equal to 10. And as a result, this inequality will hold. And then we can substitute the expression for S of S. And we will get and find the limit as S goes towards 0. We will have steady state error being equal to 10 over 1 plus 10 GC tilde, where GC tilde is the generalized gain of the controller, and it should be smaller than 0.1. And as a result, GC tilde should be bigger than 9.9. If we have this situation, the requirement on the steady state error will be satisfied. Now we have two main options. One option is to use a type 0 controller, so we don't increase the type of the system. In that case, we need to have the generalized gain bigger than or equal to 9.9. For example, we can pick the controller in the form of a proportional controller with GC1 of S equal to 10. In this case, if we use the proportional controller, then we will push the amplitude plot upwards by the given amount, by 20 decibels, and then as a result, the steady state error requirement will be satisfied. The second option would be to use a type 1 controller, where we place a pole of the controller at the origin, and the controller in this case will be in the form of GC1 will be equal to GC tilde over S. So the generalized gain in this case will be a free variable. Because the type of the system will be increased by 1, the steady state error will be already equal to 0. And then we can use the GC tilde for other purposes. In this example, we are going to follow the second case. So we will have a pole at the origin to make the steady state error equal to 0. And for that, we can use a PI controller. So we are going to use a PI controller with a pole at the origin. And for this, we need to determine a location for the 0. The 0 of the controller will be located somewhere at the low frequencies in order to not to change the high frequency part of the body plot for the system. We can see that the crossover frequency for this system without the controller, or let's say GC equal to 1, we have this blue graph for the body plot of L of j omega. We can see that the crossover frequency here is equal to 0.402. It's written also here. At that point, we have the phase margin equal to 18.6 degrees. So we need to pick a location for the zero of the controller such that it is much smaller than this frequency, and as a result, the high frequency part of the frequency components around the crossover frequency will not be touched. We can pick the zero at 0.1, minus 0.1, and in that case, 0.1 is here. In that case, as for the amplitude graph of the PI controller, we have it in this form. So we will have 0 dB after 0.1, and before that we will have the slope of minus 20 decibel per decade. So this will be our PI controller. That's what we have in terms of the amplitude. In terms of the phase, we will inject minus 90 degrees at the beginning. Around that corner frequency, the phase will become minus 45, and eventually it will go to 0. So this will be the phase contribution, and we can see that around the crossover frequency, the amplitude will not be touched, so it will remain almost the same. But in terms of the phase, some negative phase will be injected, and as a result, phase margin might become worse. So let's see how this will affect our system. So for the PI controller, again, we have placed the 0 at minus 0.1. And in order to have the amplitude of the PI equal to 0 dB or 1 after that frequency, we will have the PI controller in this form. So 0.1 times 1 plus 10s over s. Or in other words, GC of s will be equal to s plus 0.1. So in this case, as s goes towards infinity, amplitude will become equal to 1 or 0 dB. And now our L of s, which is equal to GC times GP, will have this form. So the 0 at minus 0.1 will be cancelled by the pole of the system, of the plant, and we will get L of s equal to 1 over s times 1 plus 5s times 1 plus s. Now, this controller satisfies the requirement on disturbance and noise attenuation. We were already fine with the noise attenuation. In terms of the disturbance, now you can see that as this part of the controller is introduced, amplitude will move upwards for the frequencies smaller than 10 to minus 2, and therefore the requirement on the disturbance rejection will be satisfied. We also are satisfying the requirement on steady state error, because the error now is equal to 0. But the crossover frequency now is equal to 0.4 radian per second almost, and the phase margin will not be satisfactory. In order to increase the phase margin, we could try to decrease the crossover frequency, because you can see that as the crossover frequency decreases, as we move in this way, the phase margin will increase. And since the requirement, one of the requirements here is to keep the crossover frequency bigger than 0.2, we can try to make the crossover frequency equal to 0.2, or a little bit, just a little bit bigger than that, in order to make the phase margin the biggest possible value. Let's see what's the phase margin that we have right now, and then we will see whether introduction of the PI controller has changed it or not. So without the PI controller, the original system with GC equal to 1, we had phase margin equal to 18.6, and the crossover frequency was 0.402. After introducing the PI controller, as I just explained, the crossover frequency has moved a little bit, just a little bit, towards plus infinity. So crossover frequency has increased a little bit. And since we have also introduced some negative phase into the system, the phase margin now has become very small, quite small indeed, yeah, 3.94. So this is indeed the effect of having the PI controller already. But now if we try to make the crossover frequency equal to 0.2 instead of 0.4, we can already see that here the phase margin will become bigger. Now let's see how we can make it, yeah? In order to make the crossover frequency equal to 0.2, what we need to do is to check the actual value that we have here. With the PI controller, we have okay, let me go to the proper place. I think I just jumped to some other page by some chance. Okay, all right, here we are. So we check to see what is the actual value for that frequency currently. And then after finding that value, we just introduce the proportional controller in order to push the amplitude plot downwards and then make the crossover frequency equal to 0.2. And that's what you see over here, yeah? So we check the amplitude of L of j omega at 0.2. It is equal to 10.8 decibels. Now we want to have 0.2 as the crossover frequency. Therefore, we need to push down the amplitude plot by this value, introducing minus 10.8 decibels. And the controller, therefore, will be multiplied by 0.288. This is indeed equal to minus 10.8 dBs. And therefore, the controller will be in the form of 0.2884 times the initial controller that we had, the PI controller that we had, and therefore we will obtain GC equal to this expression here. And the new L of S will be in the form of 0.2884 over the denominator. Now with that, if we introduce that, and you can see it over here, and we have it in red color, you can see that now the phase margin has increased. It's equal to 33.7 degrees instead of 3 degrees that we had originally, and the crossover frequency is equal to 0.2. So now, this controller is satisfying the requirement on the noise attenuation, on the disturbance rejection, on the steady state error, and also on the crossover frequency, but our phase margin is not enough. It's 33.7, while we need to have the phase margin equal to 60 degrees. So we need to have 60 degrees for the phase margin. Currently, we have a very small, let's say, phase margin for the system. So we need to inject some positive phase. You should know that one way to do this is to use a lead compensator. For our lead compensator, we need to calculate the location for the zero and the pole. These are the locations for the zero and pole, and I will show you in the next slide how these are obtained. And then we add it to our existing PI controller, and we will have indeed a practical PID controller, where GC of S will be in this form and L of S will be in this form. Now let's see how the zero and pole of the controller are calculated, of the lead part of the controller are calculated. So we know that omega c is equal to 0.2, that's the desired crossover frequency. We keep omega m of the controller equal to that value. So we have omega m. Then we need to determine the phi m, how much phase we need to inject, how much positive phase we need to inject to the system. The current phase margin is equal to 33.7. We find phi m in this way. The new phi m, or the desired one, minus the current one, plus some additional 5 to 12 degrees. The desired one is 60 minus the current one is 33.7, and then we add 5 to 12 degrees, and therefore at the end we will have phi m equal to 35 degrees. Now that we have value for omega m and phi m, we just refer to the formulations that we have and obtain the location for the alpha first. Alpha will be obtained as 0.27, and then we will have a value for p, the location of the pole of the system, and at the end the value for 0, and you can see that they are obtained in this way. So 0 will be equal to 0.1 and p will be equal to 0.38. And our controller will have this form, which is a practical PID controller. Then we need to check whether all the requirements are now satisfied or not. We know for sure that the requirements in terms of the disturbance and noise attenuation will be satisfied. Steady state error will be also satisfied. We just need to double check the phase margin and the crossover frequency. We can refer to the body plot that we have here. We have the crossover frequency equal to 0.358, and phase margin now is equal to 40.8 degrees. This is indeed smaller than what we expected, but the main reason here is that the crossover frequency has increased to 0.358. If you manage to move it back to 0.2, the phase margin that we will have will be this value, and hopefully it will be satisfactory. How we can do it? We can just move the amplitude plot a little bit downwards. We know that at that frequency, at omega equal to 0.2, we have the amplitude equal to 5.91 dBs. If we inject minus 5.91 decibels as the amplitude, then the crossover frequency will become 0.2. It is 0.2 ECM. And that's equal to 0.5. If we introduce that into our controller, if we multiply the controller by 0.5, we will end up with this controller, GC of S, which is again a practical PID controller. And with that, all the requirements are now satisfied. We are fine in terms of the disturbance and noise rejection and attenuation. We are fine in terms of the crossover frequency, just a little bit smaller than 0.2. We can still make it bigger than 0.2 without losing the requirement on the phase margin. And we are also fine in terms of the steady state error. So in this way, we have designed the controller, and you have seen the approach. You start by a first order controller. We just satisfy the requirement on the steady state error initially, and then we manage to do it for the other requirements and as well. Alright, so that's all for this video. I hope you have got the main approach, the steps that you need to take in order to design the controller, and you can already see that designing of the controller is usually an iterative approach. You design, you check whether the requirements are satisfied or not. If yes, you are done. If not, you just go back and adjust some parameters. Okay, so thank you for watching, and see you in the next video later.